Hello everyone and welcome to my video explaining how DCOs work, digitally controlled oscillators. I usually do synth repair videos, but with a bit of a difference. I'll choose a circuit that I like and I'll explain in detail how it works. Either a circuit I'm having trouble with or one that I find really interesting. And so when I came across this SX240, I thought, wow, good, it's a really great chance to do DCOs because I'm fascinated with DCOs. So I thought that I would explain how it works. But when I studied the DCO in this synth, I found that it was quite different from the Junos, or it borrowed some parts of early and late Juno circuits. And that got me interested, and I had a look at the AX80, and there was also more differences. And I thought it would be good to do a video that just describe DCOs in general, and then comparing the designs in all the different synths, because quite a popular topic at the moment as well because of the Behringer DeepMind 12. It's being released as a DCO synth. After studying those earlier synths, I might give my thoughts on the Behringer. So I thought I might explain how VCOs work, so the normal voltage controlled oscillator. And I'll do that as quickly as I can, and so that can form the basis for the knowledge that we can then use to go into DCOs a bit deeper. Okay, so starting with analog oscillators, you'll find on most oscillators there's a choice of different waveforms, but they're not all oscillating independently. If they were all independent oscillators, they'd all be slightly different frequencies, and it would be difficult to get the same tuning when we switched between each one. So what happens is that we have one main oscillator that controls the frequency where all our control voltages go to. And then we wave shape into other waveforms, and that keeps all of them synchronized together. Now you can start with whatever waveform you like. It can be a saw or a triangle or a square. Most commonly, the trend is towards triangles. But initially, especially in the 70s and 80s, saw calls were really dominant. And by far the easiest wave to start with is a rising saw. The circuit's actually really simple and it's really easy to control. They're quite stable and their tracking's really, really good. And DCOs all start with saw calls. Now it can be a rising saw or a falling saw, it doesn't really matter. But it's this ending of the wave is what we synchronize in a DCO. So what we're going to do now is have a look at the analog circuit for a rising saw, because once we understand how that works, DCOs become a lot easier to understand, because a DCO is basically just a saw core with major parts of that circuit just unplugged and replaced by computer control. Okay, so this is part of the schematic of the VCO of a Jupiter 8, and the reason why I've chosen it is because it's laid out really nicely in different sections, and also it's very, very similar to the saw wave shaper that's used in a DCO. So this is not a Roland circuit, it's actually a circuit that you'll find in a lot of other synthesizers. Both rising saw and falling saw can use a variation of this circuit. And I know it looks really, really difficult to understand, but really it's just like Lego. So you've got separate sections of the circuit that do separate things. So here is our saw core oscillator. And over here we have our current regulation, which controls the pitch of the oscillator. And over here we have wave shapers. So this is the triangle wave shaper, and then we've got the pulse and the square down here. So the only part we're really concerned with at this point is this saw core oscillator. And the part that's in DCOs is only actually this section. But to explain how it works in a DCO, I'm actually going to explain the whole thing. So it starts off that this op-amp puts some current into the circuit that's kind of relative to what's going on out here. You don't really need to understand how that works at the moment. So what happens is we start from ground and we start building up voltage in this circuit as we put current in. So the saw keeps rising and rising, and so the voltage in this section and this section keeps going up. And it keeps going up and up and up and up and up until we get to a point that we're comparing it to. So this is an op-amp that's configured as a comparator. And our reference voltage here is about 10 volts. So our supply voltage is 13, and if you divide a 10 and a 3K resistor, you end up with 10 volts here. So on our non-inverting input, our comparison, we've got 10 volts. So while we're underneath 10 volts and this saw is building up, the output of this op-amp is going to be negative. So you can see up here, we've got negative voltage. So as we're building up, there's a negative here. Now that negative is important because as we build up voltage in here, some of that voltage is going to skip across this resistor and potentially turn this FET on, and we don't want that to happen just yet because this voltage, the reason why it's building up is because it's storing in this capacitor. So as we put in current into this circuit, voltage builds up here and we get our rising part of our saw. Now if this FET turns on, that capacitor gets immediately shorted out and that voltage turns to zero really, really quickly. So that's the end of our saw. So we don't want to do that until we've actually hit 10 volts. So as we're going up and up and up, this comparator keeps this negative. And so any positive voltage that skips across this resistor that might turn this on actually gets sucked out into this line. So this side is at negative 13. Any positive, like 5, 6, 7, 8, 9 volts that's building up, that goes across this resistor immediately gets sucked out into this line and away from this FET, and it keeps this off, and that allows our voltage to keep building up. So once we get to 10 volts though, we get higher than our reference, and this op-amp says, oh hang on, our input now is higher, it's 10, so my answer is a positive. So then it puts out a positive voltage. In this case, it's about 13 volts. This line fills with 13 volts. And so now the voltage that's coming across into this wire here can't escape anymore because it's more positive on this side. So it's forced around to the gate of this FET and turns it on. And that shorts this capacitor, and immediately we get a return to zero. So the parts that are important in this circuit are the fact that our rising voltage in the saw is allowed to rise to a certain threshold, and that's set by this comparator. So anything under 10 volts is allowed to continue. As soon as it gets to 10, this switch, you can look at it as a switch, turns this FET on, which shorts it out, takes it back to zero, and the whole thing starts again. Now the reason why the whole thing starts again is once it's shorted, this goes to zero, and this point's now 0, which is less than 10, so our output changes, and this switch is now turned off. So this is actually really great. Sounds really good. Problem is it does drift a little, and that's because of the current that's coming in. It's hard to control the current very accurately here. And the reason why we get different frequencies is if we let in more current, we build up faster to our 10 volts. And the faster we get to 10 volts, the faster this switch shorts out the capacitor and it decreases to 0. So the way to increase the frequency is to build up the charge in this capacitor faster so we reach 10 volts faster. The way to get lower frequencies is to let current in more slowly so that we build up slower and we get to 10 in a longer time. But our reference voltage is 10. It'll never ever switch to 0 until we get to 10. So the two key points here to remember is that one is our level is 10 volts before it switches to 0, and the other way that the way that we get it to 0 is to actually short out this capacitor. So how does that relate to DCOs? Well, to control this frequency with much more accuracy, the easiest way to do that is remember that the end of the saw wave is actually where we short back to 0. So if we just disconnect this wire and connect it to a computer, we can short this out whenever we want, and we can do that really, really accurately. So DCOs, the main premise is that we just short that wave out whenever we want. So now that we have control over this, we no longer need this part of the circuit which determines when the switch turns off and on. So we can get rid of this part. The wave shapers we still need, because after we get our initial saw, we still need to shape them into other waveforms. Theoretically, we don't need as good control over current anymore. In the analog version of the saw, current is really important because it determines our frequency. And so if the current changes, our frequency changes, and that's the main reason for instability. Now that we're controlling that really accurately by cutting the saw off whenever we want, we don't need as much control here. So initially you look at this circuit and you go, oh, we don't need that bit either. But the devil is in the detail. And this is where we discover our first problem with DCOs, and that's that we need 2 points of control, not one. So if you imagine this as a VCO, all we have to do to increase the frequency is increase this rate of charging by putting in more current. If we put in more current, we charge the capacitor quicker, we reach the threshold quicker, and we cut the wave off quicker. And so we've got a higher frequency. Now, if we just do our chopping via the DCO, so if we just chop this earlier, watch what happens. So if we want a higher frequency with a DCO and we just chop, say we chop at this point, we terminate the wave and we go back to 0. That's great. And it starts charging again, and then we terminate again, and it starts charging again, and then we terminate again. But look at this wave. It's at a lower amplitude. So the problem with only chopping the wave up is that we have loudness problems. So higher frequencies would be a lower volume. And let's say we wanted a lower frequency than this current one. If we were still charging at the same rate and we wanted to chop it here, what would happen is that we would reach the maximum voltage and then we would have nowhere else to go. So the wave would actually start to distort. And then by the time we chopped, we got the top of it missing. So unfortunately, we can't just rely on the computer control of ending the wave early. We also need to control the rate of charge. So if we wanted to chop that wave early, we would also have to send in more current so that we built up quicker and approximately got to that level before we chopped. So unfortunately with DCOs, not only do we have to control our rate of ending the wave, we also have to control the current that goes in. Now the consequences for not controlling the rate of charge are even more disastrous on a negative sawtooth. So if this is our ground level here, 0, and this is say 10 volts, so we're basing it on something like the Jupiter 8 levels, 10 volts and ground. If we don't control this rate of charge and we just chop, the result of chopping with a falling sawtooth is that we end up going back to 10 instead of 0. So not only do we have an amplitude problem, but we also have an offset problem. That's way too high above 0. It's difficult to work with. We would need to shift that level back down. So unfortunately, the circuit that regulates our current and gives us approximately double the current when we need double the frequency, we can't entirely drop that with a DCO. Or at least initially, the first few designs of DCO still kept this circuit quite similar to this one. Later on, the computer control just handles entirely the current, but the calculations become a lot more complicated. So early on, this circuit was still kept. Okay, so we're nearly there. We've nearly explained the DCO. This is the block diagram for a basic generic DCO, you could say. So there's our reset signal that comes from our highly accurate clock and resets our saw wave and gives us our frequency. And here's the current coming in that's usually calculated sort of by the CPU as well. Depends on the synth, but that compensates for the amplitude and offset issues that we have when we reset our saw artificially. And then after that, we just wave shape into whatever we want. Now, the reason why DCOs are preferred over VCOs in some cases is that they're more stable. The reason why they're more stable is that each oscillator, so if you've got a 6-voice synth or an 8-voice synth, that could either be, you know, 1 oscillator per voice or 2 oscillators per voice. So you could have a lot of oscillators, and normally they'd all be oscillating at their own pitch, and they'd all be varying their own ways depending on the temperature. So it's not very stable. What makes a DCO so stable is that all of these voices are referenced to one master clock. So nothing actually oscillates by itself. In a DCO synth, you only have one oscillator, and it's the reference oscillator, the master oscillator. And this is usually a highly controlled digital oscillator in most cases. And how we generate the frequencies for each voice is that we divide that master oscillator down to a lower value. So when we press a key, the CPU calculates how much we have to divide that master oscillator by and ends up at a division that's close to our target frequency, and then we use that to create the saw. And here's where we discover another problem about DCOs, and that's we can only divide the master clock by integers because we can only count individual pulses. We can't count in between them. And that's a problem because it means at some frequencies we may not be exactly in tune. So let's do an example. So we're playing a Juno 6 or a Juno 60. The master clock frequency is 1.9 megahertz. And say we want to produce a C8. C8 is 4,186 hertz. So to find out how much we need to divide the master clock by, we just divide these two numbers. So 1.9 megahertz divided by 4,186 is 454.37, which means if we want to generate our target frequency from this master clock, at every 454.37 pulses, we need to emit our own pulse. The problem with that is we can only count to 454 or 455. And that poses a problem because neither of them are right. So if we use every 454th pulse to generate our frequency, we end up with a frequency that's too high. We haven't divided it enough. And if we use 455, we end up with a frequency that's divided too much, so it's too low. Now luckily, the Juno 6 and 60 won't let us press a C8 key. But the point here is that this is not continuously variable. They're fixed numbers, so at high frequencies we're always going to be a little bit out. Now the way to compensate for that is to make our master clock so high that we have to divide by numbers that are so large that we get really good resolution here. But that poses a massive problem in itself, and that's at the time these synths were made, we can only get 16-bit counters, which means the highest number we can count to is 65,535. So if this clock frequency, the master clock, is too high, we'll never be able to count enough to divide low enough to get to the lowest frequencies on the keyboard. So it's a trade-off between having this master clock as high as we can to get good resolution on our tuning and having it low enough so that we can still count enough to get to our lowest notes on the keyboard. Because there'll be a point where we just get to a number that's too big and we can't count that high, so we wouldn't be able to generate a low enough frequency. And that's a real problem, particularly with the Juno 6 and 60, and you'll notice that it doesn't have keyboard scaling. Now in the Juno 106, that was handled by having a higher clock frequency, which was 8 megahertz. And you end up, when you do the scaling for the keyboard, it actually divides this down to 4 megahertz and 2 megahertz. So it kind of gets around it by adjusting the master clock frequency. But still, it's not ideal. Okay, we've finished the basics, which means we're up to the fun bit. We get to compare synthesizers. So the Juno 106 has the highest master clock. So that means it's the most likely to be in tune. The Korgs have the lowest, so they're less likely to hit the exact frequency once they divide down. Now, really high frequencies also cause a bit of a difficulty when we want to divide down to the low frequencies. So the Juno 106 and the AX80, they both divide down this master clock to help reach lower frequencies, whereas the Korgs don't need to do that because they're quite low already. So potentially the Korgs could produce lower notes if all of these were using the same 16-bit counters. Now there are synths here where the frequency is fixed, like the SX240, so we can't divide down to get more ranges. We would have to do all our pitch changing in the CPU, and there's not much of that available. So there's no keyboard scaling here. The keyboard scaling is usually a range change on the clock. Same with the 660, there's no keyboard scaling, but you can transpose by an octave. And the Korg Poly-61 and Poly-800, they can change their DCO tuning. They've got a few ranges there, but that's all done in CPU. So there's an even bigger difference though than the master clock frequency and how good they're in tune or not. But to explain that, I need to open a really big can of worms, and it's over here. And there it is, there's our can of worms. And we need him for the next bit, because we're going to investigate whether DCOs are analog or digital, because it turns out they're actually one or the other depending on the synth. So, you might have remembered from the start of the video where I was talking about VCOs and how these are the oscillators in VCOs. Normally square, or you can have triangle or a saw wave or whatever. Once you turn the VCO off, the wave shapers stop. So this wave is really important. If we take that away, our wave shapers are useless. In DCOs it's similar, but we draw that uselessness much further down the chain. If we take away the counter, this saw wave stops because it's not a VCO. You'll see a lot of explanations about DCOs on the web explaining that they're saw core oscillators, which they're not. They're clearly not, because if you take away the counter, they stop. They're just wave shapers like all the other wave shapers. Just because the circuit looks like a VCO doesn't mean it's a VCO. In fact, it's the same with all the wave shaping circuits. They look essentially like their VCO core equivalents, but with bits unplugged. So this is the same. But electronically, these are all wave shapers. So let's have a look at the counter. If we take away this part of the equation, the counter stops and the sub stops. So this is not a VCO or an oscillator either. In fact, the best analogy for the counter is that it's identical to a sub oscillator. Because the way we would get a sub is, say, on every positive edge here, a flip-flop would change state. So on this positive edge, we get a change to the positive. On this positive edge, we would get a change to the negative, and we would divide down our frequency. Now the counter is doing the same thing, except it's programmable and we can divide down a lot larger than the sub. But essentially it's the same theory, it's exactly the same. So DCOs, really, the control component is just like a sub oscillator. So then we come to our master clock. This is the only oscillator in this diagram. So this is the only part that determines whether we're actually analog or digital. And the shocking part is that DCO synths are divided into two groups. One of them, the master clock, is a quartz crystal locked oscillator. And that is a very precise frequency, and it's what we usually use to do the clock on processors and all digital stuff. So they can be considered digital. The other group, the master clock, is analog. And not only is it analog, they're mostly voltage controlled analog clocks. Think about how important this is, because any variations or instability in an analog clock here will filter down the chain. If there's any slight frequency variations, the counter will divide those frequency variations, so they'll turn up here, they'll turn up in the sub, they'll turn up in the first wave shaper, the saw, and they'll turn up in all the other wave shapers. So if this is slightly a little bit unstable, or if we deliberately change the frequency here, then everything else is affected. Whereas if this is a really highly precise crystal oscillator, well, everything else is really highly precise. Now we can use this design choice to our advantage. So if we use an analog clock, we can affect that analog clock by external CV. So we can add bender and LFO or vibrato, whatever you want to call it. We can add external CVs to vary this analog clock that will then vary our oscillator frequency. Or we can choose a crystal clock and we can get higher frequencies and better tuning and more stability. So it's really just a choice. So the Juno 660, the Poly-61, the Poly-800 all have analog master clocks. I'll spell it the American way because I'm running out of room. And these ones, the Juno 106, the Kawaii SX240 and the Akai AX80 are all digital crystal oscillators. So there's a very big difference between the Juno 60 and the Juno 106. And I've had heaps of people say, oh, the 60 sounds better. There's something about it. Maybe it's the envelopes. Maybe it's something like that. And I'm like, no, it's all the same. It's just DCOs. Well, fast forward to 2016 and I'm studying DCOs. And there's a very big difference. The Juno 106 is highly precise crystal clock. And the Juno 6 and 60 are analog. So there you go. Okay, so let's quickly have a look at the schematics for some of these synths so we can compare the differences. So this schematic is for the JU6, which is Juno 6. You can see down here we have our analog clock. So in the other synths that have the crystal oscillator, this entire circuit would be replaced by the crystal oscillator. But the advantage of doing it this way is that we can control it by a control voltage, and we can change the pitch depending on what the bender and the LFO are doing. So this clock varies in frequency depending on the modulation sources, and it goes into these two counters. So these counters are what divides that frequency down to do our pitch for each key. You can see channel 1 comes out here and up here, and this is our input for the DCO, or this is the DCO waveform. That is kind of like a square wave, but it's just one pulse every 4,000 or one pulse every 400 from the master clock. So it's not really square, it's more like kind of like a trigger, but it's still in the shape of a pulse. So this capacitor here shapes that into more of a trigger looking pulse. So it goes from looking something like this to looking something like this, which is more of a trigger. So that trigger comes in here and it actually turns off this PNP transistor. So this works in the opposite way of the Jupiter 8, which I showed you, which was that we kept this closed and we built up charged here, and then we opened it and shorted the capacitor out, and that would give us a rising saw wave. But this is a falling saw wave. So the way it works is that we close this, we build up charge really suddenly, and then for the rest of the time it's actually open, which is the opposite to the Jupiter 8. And while it's open, the capacitor is constantly discharging through this resistor. So we're constantly discharging, and the only time that it's not is when we actually turn it off, and then it quickly jumps back up. So it's kind of the opposite. So what we do in this is a sample and hold circuit, is we preload the CV for each channel that we need. So if we've got a high frequency, we would need this slope to go down quicker. So we put in less current and this capacitor discharges quicker. And for the lower frequencies, we actually put in more current and we prevent this capacitor from discharging quickly. So it's kind of the opposite to Juno, to the Jupiter 8. But this falling saw actually sounds really good. In fact, I think that generally speaking, falling saws have more bass in them or less high frequencies. They just sound fuller in the lower end. So that may also contribute to the Juno 60 sound. Okay, so that's our saw shaper. Here you see our flip-flop. So that's the sub-oscillator, that's pretty obvious. And down here you've got the comparator, which is comparing this saw wave with a constant voltage, and that produces our pulse width modulation. So the way pulse width modulation works is if you compare just set a high voltage on the comparator, only the tops of the peaks will end up with a positive, so you get short pulses. But if you set a lower voltage on this comparator, the lower voltage means that it'll be on for more of the saw, so you get a wider pulse width. All the waveforms are combined at this point here, and then they're fed into the filter. So that's the Juno 6. So the things to take away for that are just the analog clock, really, and the fact that the waveform here is a falling saw. The only other synth in this group that I'll show you that has a falling saw is the AX80. And the AX80 does it completely differently. It actually does it more like the Jupiter 8, but completely inverse voltages. So this is done negatively, which is a much smarter way to do it. But still, Juno 60 sounds awesome. Okay, so here's the schematics for the Juno 106. It's vastly different to the 6 and the 60. So you can see up here, instead of having that huge analog clock, we've just got the one crystal, and there's some impedance boosting circuitry here. And then this is our first divider, and this divides for the range. So this divides the clock from 8 to 4 and to 2. So we've got to select lines here for the division, and these continue all the way to the chip that selects the different resistors, because every time we change the range, we also need to change the current that goes into this saw, because it'll be different. So we select our initial clock division here, and then it's sent down into the counters. So these are the two counters that do our 6 voices. And then after the DCO counts them, it's sent into this chip here, which is basically a whole big, huge wave shaper chip, which does all our waveforms at the same time. And that looks like this internally. So we've got our DCO. And see how Roland's even labeled it DCO here. And in fact, in the 6 and 60, Roland's labeled the DCO as the sub-oscillator, if you read the schematic. So I don't think they were even sure what the terminology would be or which parts they were describing that early on. But by this stage, the term DCO pretty much referred to the frequency that's coming out of the dividers. So here we have our range resistors. We have our pulse here. There's that capacitor that changes our square into more like a trigger. Now this is a rising saw, so it's the same as the Jupiter 8 direction of the saw wave, and completely different to the 6 and the 60. The 6 and the 60 were the falling saw. So this is a more traditional circuit now, and we're actually shorting this cap here. So it's connected here and here. So we build up our current into the capacitor, and then the short comes in and shorts this out, and we go back to 0. So down here we have our pulse width modulation. So again, it's just an op amp configured as a comparator. We put in our voltage here of where we want to take the level from the saw. So higher we'll get a narrower pulse, and down lower we'll get a thicker pulse. And the way we turn the pulse off is to increase this voltage so much that our reference goes above the saw. So the saw never peaks above that reference voltage, so the pulse never turns on. So the pulse only turns on once the saw gets higher than the reference. That's how we set the height or the width of the pulse. So if we just set that so high, we'll never get a pulse. So it turns off here just by this control voltage. And the way we turn the saw on and off is just we short it to ground. So the saw comes out here and just goes straight to ground instead of to the output. So that is the 106. Okay, here's the schematics for the Kawaii SX240, and this is our master oscillator. So it's a 12 megahertz crystal, which is later on divided down to 4 megahertz to run the oscillators. But it starts off at 12 because not only does it run the oscillators, it also runs all the CPUs. It runs the master CPU and the slave CPU. So it runs all the digital circuitry in the synth not just the DCOs. So after we get a bit of a boost in current here, it goes to both the chips, and down here where it's divided to 4 megahertz, and it's this 4 megahertz signal that we use for the DCOs. And the DCOs, where are they? Here. So these are our divider chips, are different to the Junos. The firstly it comes into this pre-scaler, but that's mostly just for the DCOs. There's 2 oscillators per voice, and they're pre-scaled. You can drop the lower split by an octave, and you can do some things here, but it's not like the range that the Juno has. Then of course they all come out and go off to our analog circuitry. And initially this circuit looks really familiar. You can see the sub-oscillator, which is our flip-flop. You can see our comparator that compares the saw wave to a fixed voltage and sets our pulse width. And then this circuit, which obviously is the saw wave generator. But here we use a PNP, a transistor, instead of the NPN. So the NPN would be normally off. We would build up charge here and we would send in a pulse to turn it on, and we would short it out. But Kawaii are using a different voltage to trigger it. So they've used a PNP, which means it's normally on, but they're holding it high. So there's a high voltage here which holds it off, and then a low voltage trigger actually then turns it on and shorts it out. So the control is the inverse to the Juno and the Jupiter, but the effect is the same. You end up with a rising saw. So after all our wave shapes, we get a rising saw, our sub, and our pulse. They go into the filter chip over here, which is the SSM2044. And that's it for the SX240. Okay, so we're up to the Akai AX80, and this is the block diagram of the CPU board. So here's our clock, and then the first thing that happens is our clock is divided down to create the ranges on the keyboard. So this is just like the Juno 106, and then that pre-divided clock signal goes into our counters, and it counts 1 every 400 pulses or 1 every 4,000 pulses, depending on the frequency we need, and emits out here. And here's our first 2 saw shapers for DCO1 and DCO2. So the DCO frequency comes in here into this transistor. Now, according to the manual, this is a falling saw, and I don't have an AX60, so I can't confirm it, but this falling saw circuit is different to the Juno 60. And in the Juno 60, we were controlling the discharge of this capacitor. So the capacitor was discharging through this transistor, and we were putting in current to control that discharge. Now this is different. This circuit works similar to a rising saw in that we build up charge and then we short it out. So we don't have a resistor controlling the discharge of this capacitor. There's nothing here. So as soon as we activate this transistor, it's going to short that out. So the way we create a falling saw with the same circuit as a rising saw is that we invert all the voltages. So this runs negatively, and that looks like this. So we start from ground, we build up negative charge, and then we short back to ground. So that's the mirror image of a rising saw, where we would build up charge and then short back to ground in a positive way. This is much better than doing it the Juno 60 way, because we don't have to control the rate of discharge coming back down. We just short. It's much easier. You don't have to worry about the level. It's not like the AX80 emits negative voltages or anything. They're all balanced later on. So the output's the same. So we have a look back at our wave shapers. So at DCO1 here, this is a PNP transistor. So we'd need a more negative voltage coming in to short that out. So with more negatives building up here, if we hold this at ground, this is off. Then we have a more negative coming in and we short it out. Now you can see up here at DCO2, there's these diodes blocking, and you can see that it's facing this way, so it's letting a negative in to control this transistor. And there's another one here too, that's for the hard sink. So we get a hard sink control, which takes over this transistor as well. So that's it for the AX80. So we're done, because I'm not going to do the Korgs, because the schematics for the Korgs were just too hard to read, and that just won't work out on video at all. So a few quick thoughts on the Behringer, mostly to do with frequencies. What I would do if I was them is get the highest clock speed that I could. Now they could go much higher than this now, but I would say even 16 megahertz probably enough. And then use a chip with a really large bit depth, because the problem with high clock frequencies with these synths is that we couldn't count to high enough numbers to get to low notes, but they're only 16-bit counters. So if Behringer got something like a 32-bit counter or you know, even 64-bit processor, whatever processor they're using, it'll be higher than 16-bit. So they'll be able to count much, much higher numbers and lower frequencies. So they could use a higher clock speed, get better resolution on the tuning, have bigger counters to get down to the lower notes, and then they could actually do all their CVs and manipulations of the frequency inside the processor as well. So you wouldn't be using traditional counters, you'd be using software for all of that. So to compare it to another synth, the Juno 106 would be probably closest, and they did say that. So you would have the CVs coming into the CPU recalculating everything, and then the counter itself would be doing all the hard work. So there'd be no need for pre-dividers anymore, and you'd use a crystal. You wouldn't use the analog clock. And then in the Juno, this was a wave shaper chip, but you could do this fairly simply with cheap components. So although it is 12 voices, but I don't think they would have made their own chip. This will be discrete components. So that's it. So hopefully it sounds good. And I hope you've enjoyed the video on DCOs. It's been fun, actually. I've always wanted to do one on DCOs. So, okay, here's a quick test to see how much you've learned. How many oscillators does this synth have? It's an 8 voice with 2 DCOs per voice, maybe 16. I'll show you. 1 here, that's it. That's the one crystal oscillator in the SX240. And here's all our counter chips. So there you go. Thanks for watching, and hopefully see you in the next video.